Dear viewers, thank you for watching this channel. You're welcome to Linear Programming Primal and Dual. In this video, we shall be talking about how to convert a linear programming problem that is primal to dual and vice versa. At the end of this lesson, learners should be able to convert primal linear programming problem to dual linear programming problem, which is from minimization to maximization. And also, you should be able to do the other way around, to convert dual linear programming problem to primal linear programming problem, which is from maximization to minimization. I remain your operation research facilitator, Abdullah Okoyemi Falade. The concept of primal and dual. Every linear program is associated with another linear programming called dual. The original problem is called primal. That's the linear programming of primary interest, the one that is extracted from the real life problem. And the inverse is the dual. The optimal solution of either problems reveals information concerning the other optimal solution of the other problem. By this, what do we mean? If the optimal solution of either primal or dual is known, the optimal solution of the other is also available. Now, how do we obtain a dual problem from a primal problem? Step 1. To make life easier, you need to rewrite the given primal linear problem in matrix form. You shall see this in the example. 2. You determine the number of constraints you have in the given primal linear programming problem. And having the number of constraints will determine what is going to be the variables, the number of variables that you will have in your new problem, which is the dual. Then you need to transpose the left hand side of the constraint matrix. You shall see this in our example. And then you can transpose the right hand side of the constraint and replace in the objective coefficient. Also, you transpose the coefficient of the objective function and replace with the right hand side. So once you do the transpose of the coefficients, the transpose of the coefficient of the objective function, you have to replace it with the right hand side of the constraint side of the new dual linear programming problem. Then you revert the inequality. Once you revert the inequality, if it is less than before, it turns to, if it is less than or equals to, it will change to greater than or equals to. That's what we mean by revert the inequality. And finally, you can change, if you're converting from mean to max, you cannot change the mean to max. If it is from max to mean, you can change from max to mean. That's what we mean by change mean to max or vice versa. If you're watching this video for the first time, do not forget to press like, subscribe, and turn on the notification bell so that you can enjoy more videos. Now, let's look at a typical example of how to apply these steps. The first one, write the dual of the linear programming problem. We have min c, 3x plus 1y, subject to. The first constraint is 2x plus 3y less greater than or equals to 2. Because this is a prime, is a primal, we are trying to convert to dual. And don't forget the constraint sign for minimization problem from the previous video is greater than or equals to. We also have the second constraint, x plus y greater than or equals to 1. And lastly, we have the non-negativity constraint as x greater than or equals to 0, y greater than or equals to 0. Don't forget, we need to rewrite this in matrix form. How do we do that? So this can be written as 3, 1 in bracket x, y. So by matrix multiplication, it's going to be 3 times x, 3x, plus 1 times y. So it's back to the original position. So this is right. We also do that to the constraint side. At the constraint side, we have the variable xy. This is 2, 3, 1, 1. So when you do the matrix multiplication, you still have this back. and you have the sign which is greater than or equals to. At the right hand side we have 2, 1, and also the non-negativity constraint. So we have been able to rewrite the given primer in a matrix form. The next step, since we have 2 constraints, so you can see now we need to determine the number of constraints that we have. We have 2 constraints, so definitely the dual we have the 2 variables. So we can now change, so you need to change to another letter. Instead of xy, we intend to change to AB. So now we can now have min C equals to 31 AB subject to. Now we are trying to take the transpose. We transpose the constraint matrix. So this is the constraint matrix. If you find the transpose, it means you turn rows to column. So 2, 3 is in the row, it will not be in the column. That's why you have 2, 3 at the column now. 1, 1 is in the row, it will occupy the column. And the letter xy has been changed to AA, greater than or equals to 2, 1. The next step, you take the transpose of the right hand side of the constraint. These are constraints. The right hand side is 2, 1 in column. If I change it to row, it will be 2, 1 in a slant form. So you replace it here at the objective function. And also you will replace, you take the transpose of this 3, 1 from row, it will become column, and it will occupy this position, which is the right hand side of the constraint. And you have this. The next thing is for you to revert the inequality. So if you revert the inequality, the less than or equals to will now turns to greater, the greater than or equals to will turns to less than or equals to. Turns to what? Less than or equals to. And the last thing is to change the mean so that it will go in line with the sign you have changed. So the mean will now turns to max. You can use max C as that. And that means our A and B also satisfy the non-negativity constraint. A greater than or equals to 0, B greater than or equals to 0. And finally, we have the complete dual linear programming. So that will be max C, 2A plus 1B, subject to 2A plus 1B less than or equals to 0, 3A plus B less than or equals to 0, A greater than or equals to 0, B greater than or equals to 0. So this is the complete formulation of the dual generated from the Primal LPP. I hope you've learned 1 or 2 things in this video. Thanks for watching. So we have this exercise for you. You can do this at your leisure time. And also, in the previous example, you can also try as much as possible to try it on your own path to convert from the maximization problem to minimization problem. Thanks for watching. Bye for now.